Module 13, which deals with Gibbs free energy and kind of everything within that formula / concept. Okay, so we're on we're on module 13, which means that we're almost done with the semester, and that's kind of insane. But module 13 deals with Gibbs free energy and kind of everything within that concept, like how to get Gibbs free energy from different things. And I know the way that our workbook is set up here at UTEP, it kind of teaches you the separate parts of Gibbs free energy. Like it's weird and not as flowy as I want it to be. So the way that I do it is that I'm going to give you guys a formula for Gibbs free energy and then explain what every component of it is and how to solve for the different components and what they mean. Cool. So the formula for Gibbs free energy is delta G is equal to delta H minus T delta S. And some of these may look familiar, some of them may not, but we're going to go through them anyway, so it's fine. So the first thing that I'm going to the first thing that I'm going to explain, it's going to be the concept of Gibbs free energy itself, the delta G, just so that you guys kind of understand what it is that we're talking about. So delta G is essentially a measurement, well, it's Gibbs free energy, first of all. Gibbs free energy, and it's usually measured in either joules per mole or kilojoule per mole. It just depends on what the problem's asking and what makes it easier for you guys, but just keep in mind your units of what you end up with when writing an answer, right? So Gibbs free energy essentially is a measure, yeah, I spelled that right, measures how spontaneous a reaction is. And what I mean by spontaneous, it's just how likely it is to happen. So spontaneous equals will happen without interference. And what I mean by it'll happen without interference is that, take for instance right now, if you were to put an ice cube outside, you would expect it to melt. But if I were to put a cup of water outside, I wouldn't expect it to turn into an ice cube because it's kind of hot right now where we are. So it shouldn't turn into an ice cube. If it does, that's witchcraft. I'm gonna go ahead and say it. It's witchcraft. But, okay. So yeah, you're just measuring how spontaneous something is, how it'll happen. And a story that I tell every semester, and it sucks that I can't see you guys in person to say this, but it's kind of like we expect things to happen just because they're supposed to happen. They're spontaneous, right? So this one time, I was helping my mom in the kitchen, and I was washing the dishes, and she was just making dinner and stuff, and she gave me like rice, I think it was, for my food. And I tried the rice, and I was like, oh mom, the rice is kind of cold, like we have to heat it up, right? And she just went, okay. So I went back to washing the rest of the dishes that were like piling up because of cooking. And my mom turns around, does whatever. She doesn't even grab the rice that was cold. Like it's straight up still on the table. And she turns to me, she looks at the rice, then she looks at me, and she says, no se calentó. And I was like, I dropped the dish I was washing because I looked at her and I was like, Mom, you didn't heat up the rice. We didn't do anything to it. It was just on the table. Like, no, it didn't heat up. And that's a non-spontaneous reaction. Like, you wouldn't expect to put rice out on your dinner table that's cold and expect it to heat up when you didn't do anything to it. So, yeah, that's non-spontaneous. Yeah. So that's my story about how my mom thought rice could heat up if she did nothing to it, but like, that's non-spontaneous. It wouldn't happen. So essentially, if your delta G is less than 0, meaning it's negative, your reaction will be spontaneous. spontaneous, meaning it'll happen. So the delta G was not negative because that wouldn't happen. But yeah, so that's essentially like delta G, how you would, well, what it means is just if your thing is spontaneous or not. So then the next thing we're going to move on to, and I'm going to need more room. Yeah, okay, is your delta H, which hopefully is familiar to all of you guys as enthalpy, which is measured in kilojoules per mole. And then with enthalpy, if you guys recall, you have two parts of it, which is exothermic and endothermic. Which, okay, I'm going to draw the graphs for you guys just to kind of a refresher of what they're supposed to look like, and just if you encounter them in an exam or homework or anything you guys remember. So this is energy, which in this case is heat, and this is your reaction progress. So I'm just going to label this as E, and then this is RP, just because it's right here. So in an exothermic reaction, you start off with more heat in your reactants than you do in your products. So your graph looks something like that most of the time. And your delta H is usually less than 0 in this case, meaning it's negative. And then endothermic, the opposite happens, where you start off with less heat and end up with more. So your delta H is usually greater than 0, meaning it's positive. So yeah, just remember that exo is negative and endo is positive. And this is what your graphs look like. So then, kind of with delta H, there's different ways of calculating it if it isn't given to you. So if you guys recall, your delta means a change in this case, a change in enthalpy. And to solve for the delta H of your reaction, so of the whole thing, it would be the sum of your delta H of your products minus the sum of your delta H in the reactants. And what the N stands for is the moles, because if you guys see, enthalpy is given in joules per mole, and that's just 1 mole, and usually you don't have just 1 mole in your reaction, you have like more, or like maybe even point something of a mole. So yeah, that's what you put in your N, and it's usually your stoichiometric coefficient, so you hardly get the point something, but just in case, you know what I mean. So yeah, that's your review on enthalpy, just that exo versus endo and the signs that it would have and how to solve for it given like a chart or something. So then the next concept in the formula is T, which is temperature. So this won't take long because you guys know what temperature is. So your temperature, and this one in this formula, we measure it in K. So Kelvin. So you have to turn your degrees Celsius into Kelvin by adding 273 to it. So just remember to convert them because they're usually going to give them to you in Celsius. So then the final thing is our delta S, which is entropy. Entropy. And it's measured in joules per mole K. And essentially what entropy is, entropy equals a measurement of how disordered a system is. So yeah, entropy measures how disordered a system is. So if you take, for instance, if your system is a solid, it's not going to be very disordered, meaning its entropy is probably going to be kind of low. Because in solids, your molecules are always kind of touching each other, right? Like there's really no room to do anything. So it's kind of like, think about it being in a really crowded room. Like, yeah, it may seem disordered to you because there's no room for you to move, but it actually is like ordered in that case because you can't move. There's no room for you to be a mess and just mess around. You're stuck there. You're very ordered, so your entropy is going to be low. So then after a solid, you have a liquid, which is slightly more disordered than a solid. Because yeah, you still have a lot of molecules, but at least they have room to flow now in a liquid. So in this case, the entropy is greater in a liquid than a solid. So then finally, you have your gas phase, which is where you have the most entropy, because we all know that gases are crazy. The molecules just be bouncing left and right. It's like if you were left alone in a really big house, you can just go crazy, jump on the bed, climb down the stairs, go down the rails. You're super disordered in that case. So your entropy increases as you get more disordered. So a solid is less disordered than a liquid, which is less disordered than a gas. And then for your reaction to kind of be favorable, you would want to be more disordered than ordered, just because you have more freedom to do things. So then let's take, for instance, if I were to ask you what the entropy would be, or which system has a higher entropy between 1 mole of solid water versus 1 mole of liquid water. So which system would we expect to have the higher entropy? Well, water, the liquid water, is more disordered than a solid, so we would expect the liquid water to have a higher entropy. So yeah, that's pretty much it for entropy. You're just measuring how disordered a system is. And just like delta H, the way to calculate this, so your delta S for reaction is equal to the sum of the delta S of your products minus the sum of your delta S of your reactants. And again, your N is the number of moles because per mole, and you're usually never given 1 mole because science is mean. But yeah, so that's pretty much it for the separate components of the Gibbs free energy concept, or formula, I should say. So then we're going to go back to this chart up here, which I kind of ignored in the beginning because we really didn't know anything about it. So we're going to figure out what the sign of G would be and if it would be spontaneous or not. So I'm going to rewrite the formula. Delta G is equal to delta H minus T delta S. Right. So then in the first problem, it tells us that our delta H is less than 0, which is a negative. So that's just going to be replaced by a negative sign. And our delta S is greater than 0, meaning that it's positive. So this is going to be replaced by just a positive sign. Because your temperature in Kelvin, you can't really get a negative because absolute 0 is absolute 0. So yeah. So then if we were to distribute this to the positive, we end up with a negative minus whatever number you would have there, which means that our delta G would be negative. So is that spontaneous or not? Well, looking over here at what I told you guys, if your delta G is negative, it's spontaneous. So yes, at all temperatures. Cool. So I'm going to erase this and go on to the next one, which I'm going to label as this one. So our delta H is greater than 0. It's positive. Our delta S is less than 0, which means it's negative. Oh wait, that's positive, my bad. So we have a positive, and then we redistribute, well, we distribute that negative. So we have a positive and a positive, so our delta G will be positive. So that means that it is non-spontaneous. Non-spontaneous in the forward reaction. So then moving on to the next problem, 3. So we have that both of our signs are positive. So we have a positive this, and then we have a negative and a positive, and we're going to redistribute that. So we have a positive and a negative. So if we were to do whatever number this is minus whatever number that is, we don't really know what the sign of delta G is, so we're going to put depends here, because this essentially is going to depend on your temperature. Because if your temperature is high enough for it to be greater than that positive, you're going to have a spontaneous reaction. So this is at high temps. And what I mean by that is, let's take for instance our delta H was a positive 2. And then our temperature was 6. And then our delta S was 1. Yeah, and they're both positive, right? So if we do that math, we have 2 minus 6, which ends up at a negative 4. So since the temperature was high enough to overcome what our enthalpy is, we have a spontaneous reaction. So it depends on the temperature, it has to be high enough. Yeah. So then the next problem, or the final one, both of our things are negative. So again, this is going to depend on the temperature. So we have a negative minus T, and this is a negative, right? So then we redistribute this, and we end up with a negative minus T. So I shouldn't put parentheses on that, because that's going to make it look like I'm multiplying. Okay, yeah. So whatever number this is minus T, so this one, it will be spontaneous at low temperatures. Just because you want this number to be small enough that, oh, that should be a plus, because I redistributed that. Yeah. So minus plus, so that it doesn't overcome your positive. So in this case, if we still had the 2, and then minus, and we say our temperature is 0.5, and our delta S was a negative 3, then we would have 2 minus a negative 1.5, which would be 2 plus 1.5, negative 2. Oh my god. Yeah, because our delta H is negative. We would end up with a negative 0.5, which it's negative. So our thing would be spontaneous because the temperature is low enough. So yeah, that's just kind of keeping track of how the signs of your different components can tell you right away if your reaction will be spontaneous or not. Because like I said, if your H is negative and your S is positive at whatever temperature, you're going to have a negative delta G. And if your delta H is positive and your delta S is negative, at whatever temperature, your delta G is going to be positive. And if they're the same side, it'll depend. So then let's do an example of figuring out how to find delta G. Cool. So, example. Oh wait, there you go. Yeah, so I have this chart just because it makes my life easier and I didn't want to write. Right. So then what we're going to find is the delta G and if our reaction is spontaneous. So is it spontaneous? So I'm going to rewrite our formula, which is delta G is equal to delta H minus T delta S. So then, oh god, that looks really ugly. So we're given all of the values here. Oh, I forgot to write down the formula. Give me a second. So the formula is 2NaHCO3 solid yields Na2CO3 solid plus H2O liquid plus CO2 gas. And okay, you guys are going to have to get your head out of equilibrium, because in this case we do count the solids and the liquids, so our condensed states, we do use their values to calculate our overall deltas. Yeah. So since we're given all of these values, we're just going to do the whole sum of it equals products minus reactants. So let's solve for delta S first by doing the sum of the products minus the sum of the reactants. So the products in this case are going to be carbon dioxide, water, and sodium carbonate. So we have 213.60 plus 69.9 plus 135.98, and none of these have any coefficients, so we don't have any moles to multiply it by, because they're all just 1. And then it'll be minus the reactant, which in this case is just sodium, I think that's bicarbonate. But in this case we do have a 2 as our coefficient, so it's going to be 2 times 102.99. And then once you do all that math, you should get around 213.47, and this is in joules per mole K. So that's our delta S, which is our entropy. So then the next thing we're going to solve for is our delta H. Alright, this is at room temperature, by the way, which is 25 degrees Celsius. But anyway, so we do the same thing, which is the sum of our delta H products minus the sum of our delta H reactants. So it's going to be negative 393.5 plus negative 285.8 plus negative 1139.9 minus 2 times the negative 947.7. And then once you do all of that, you should get 76.2 kilojoules per mole. And then our temperature is 298, well, it's 25 degrees Celsius, which we can just convert to 298. So we have 298. Let me erase that because then I won't have room. Times what we found our other thing to be. So, Jesus Christ, let me rewrite this. Alright, so enthalpy is in kilojoules per mole, but this, our entropy, is in joules per mole. So we're going to convert from kilojoules to mole by just multiplying by 1,000. So we end up with 76,200 joules per mole. And now that our units are all the same, we can plug in. So we have 76,200 joules per mole minus 298, because it's at 25 degrees Celsius. I didn't write it down, but yeah, so just convert it, times 213.47 joules per mole K, and the K's from the temperature cancel out, even though I forgot to write it down. So then you just solve through it, and you should end up with delta G is equal to 12,585.9 joules per mole. And if you just don't like big numbers, you can just write it down in kilojoules per mole, which would be 12.59 kilojoules per mole. So just as long as you guys label if it's in joules or kilojoules, it shouldn't matter. It's just a conversion factor. It should still be the same number, essentially. So that's pretty much it for delta G. And then in the next video, we'll just talk about how delta G relates to equilibrium, and it should be fairly short compared to this one.